new things. You right over there? Oh, I hate that. There's Band-Aids to the left of the sink in the math lounge in a first aid box on the wall if you need some. Yeah. All right, so describing data. So some things we went over last time, different kinds of charts. And aside from, say, bar charts and pie charts, one of the most common charts in describing data is a histogram. And usually you make a histogram by setting up what's called a frequency table first. Oops. And to do a frequency table, you have to have grouped data, and you have to decide on the groups. So we spent a bunch of time in the last class playing around with how do you set up a histogram, how do you group the data. So we'll do a little bit more of that today, after just a little bit. Other things we took a look at were measures of center. The main two being average. And here, average means arithmetic mean. That's where we add them up and we divide by how many. Okay. Not everybody uses the word average the same way. Sometimes when people are talking about average for middle, they mean median. So we're going to play around with the idea of median versus average today. And median is in the middle when the data is ordered. And one of the best things for me about describing data in this day and age is there's all kinds of computer software that just does this for us, and then it's up to us to then do something with those values. So I'm going to review how to do all this stuff on a spreadsheet. So we'll probably spend 45 minutes working here together, and then we'll jump into the lab so people can make histograms and frequency tables and averages. There's another kind of sort of measure of center called the mode. And that's just the most frequently occurring. And sometimes there's a mode, sometimes there's no mode, sometimes data can have more than one mode, sometimes it's meaningless. But average in terms of the mean and then the median are definite measures of center that we should find all of the time. And they tell us slightly different things about the data. So consider the following data. So suppose these are home prices in hundreds of thousands, right? So 100,000, 1.5 hundred,000, and so on. I'm just writing them up just to be a little easier. I have 5 numbers here. What's the median? Well, the numbers are in order, right? And I have 1, 2, 3, 4, 5 of them. And so the middle number, 2, is my median. Oops. In terms of locating the median in a set of numbers, the count for a data set is how many numbers there are. And usually we use the letter N for the count. So here the count is 5, right? To find the median, you always look in the position n plus 1 over 2. So let's see, the count here is 5, add 1, that's 6, divide by 2, and I get 3. So that throws me in the middle of the data in terms of finding the median. If I threw a sixth number into this, then there's no longer 5 items, there's 6. And so then I do my 6 plus 1 over 2, which is 7 over 2. 2 goes into 7, 3.5 times. So then I would have to look for the median between the third and fourth numbers. So in this case, so this right here tells me the position of the median. Then to actually find the median, I have to go look in that position. Now, here it's a split position because of the 0.5. So what I do is I take the third one, add it to the fourth one, oops, and divide by 2. So let's see, that's 4.5, cut that in half, and I think we get what, 2.25 would be the median here. So when we're looking at ranking things, we have to talk about the position of the item and what the item is. Okay. Now, if you remember, that should be enough sugar to get through class. Okay. When we worked on what was that, growth models, we had to deal with the recursive type equations where we have to keep track of the position of the thing and what the actual number is. So it's kind of same idea there. Question? 2, that should be a 2. I miswrote a 3 there. It should be 2 plus 2.5. Yeah. I said the third number and meant to write 2, but 3 came out of my hand. Okay. So again, when we're trying to find a median, we have to consider both the position and then find it. Now that's if we're doing it by hand. Chances are you're not going to do it by hand, but there's a few by hand computations I'm going to show you today anyway, even though we have a computer to back us up. All right, let's do something else. Let's look back at the original set. And I want to do a comparison of average and median. So my original set was what? Started with 1. So 1, 1.5, 2, 2.5, and 3. So let's consider this set of numbers. N is equal to 5, right? So the count is important. Median is usually abbreviated MED if you don't feel like writing the whole thing. And the median here, we can just look and see, oh, 2 is in the middle because they're in order. The mean, however, we have some work to do. So if you could help me figure out what the mean is here. So for the mean, remember, I have to add them up, divide by the count. So I have to figure out what is 1 plus 1.5 plus 2 plus 2.5 plus 3. And then I need to divide that by 5. So come up with something there for me. You got 2? Whoa. The mean and the median are the same? Interesting. That doesn't happen all the time. It only happens sometimes. Can anybody point out something about this data set that may be leading to those guys being the same? I have an odd amount of numbers. Okay. Okay, so the even versus odd. You don't, what's that? That was the position, yeah. Okay. Anyone else have a thought why these might have worked out to be the same? Think about how the numbers are spread out from the middle. Yeah, aren't they all equally spaced by half? Mm-hmm. This is plus a half that way. This one's plus another half that way. These, on the other hand, are minus a half that way, and then minus another half that way. And so my claim is the mean and the median came out the same because the data was equally spaced on each side, perfectly balanced. When that's the case, the mean and the median will line up. Do you think data is usually perfectly balanced on each side? Not usually, no. Okay. So that's unusual. So let's tweak the data set a little bit and see what happens. So same set of numbers, almost. Okay, so maybe these are, again, housing prices in hundreds of thousands, and there's one really big fancy house in the neighborhood. So n is still the same, right? The count, still 5. Median's still the same, isn't it?
Mm-hmm.
There's still 5 numbers. The median's still 2. That didn't change, no matter how big I made the max. However, is the mean going to change? Yeah, we just increased the sum substantially. So when we go to find the mean here, which is add those suckers up and divide by 5, what do we get? 10, 15, 16, 17, what is it? 3.4, okay. So this 10 here drug the mean out towards it. It pulled the center from where it used to be, okay? And so here, would you consider 10 to be kind of like way out of bounds compared to the other numbers? Yeah, so some people would classify the 10 as an outlier. There's mathematical ways to say, yes, it's an outlier, or no, it's not, but let's just go with our gut. 10's kind of way out there compared to the other numbers. And so when there are numbers that are unusually high or unusually small compared to the others, that will drag the mean, excuse me, away from the mean. So here I had a number that was unusually large, and notice it made the median go to the right of the mean, excuse me, go to the right of the median. Okay, so it drug it away. And what's often going to happen if we have more data and we made a histogram, so the earlier example we saw, we had this perfectly balanced data set. And so imagine we just had more numbers, then we'd get this nice perfectly balanced histogram. In a situation like that, you're going to find that the median and the mean are right next to each other, if not the same number, depending on how balanced it was. So that's one possibility. Another possibility is that you have a whole bunch of data on one side, but not as much on the other side. And so here, the median might fall about right here, but this tail out this way would drag the mean toward it. Okay? The tail stuff will pull away. And similarly, if the tail was on the other side, so if my data set looked more like that and I have a tail out on this side, the median would probably be around here, but the tail will drag the mean toward it. Is it always a guarantee that the tail will pull the mean in that direction? Well, it depends on the balance of the data. But usually, most of the time, the mean will be pulled toward the tail away from the median in the data. So when I do a calculation and I see, hey, my mean is way bigger than my median, that would mean, hey, there's some big outliers, some numbers that are way bigger than the others to the right. On the other hand, if I found the mean was quite a bit smaller than the median, that would lead me to believe graphically, hey, there's some lower end numbers that seem to be unusual compared to the rest, pulling that mean away. Right? So those are some things that we might notice when we compare a histogram to the mean and the median. All right, so let's see, some other things we need to do here. Let's take a look at some data we collected the other day. So here we have temperature from people in the class, and I think everybody in here, we had your temperature. Let's blow that up a touch. Okay. So what I want to do on this is I want to have you guys help me calculate the mean and the median. Now, in calculating the median, wouldn't it be nice if these were in order? So on a spreadsheet, if I want to just sort this stuff here, then I highlight it, I go to data, and then I want to sort range. If I try to say like sort sheet, what that will do is it'll shuffle all the rows, so this stuff will get mixed up too, and I want those to stay the way they are. So either I can say sort range, or I can say just the stuff I highlighted, sort it. Oops, I forgot to tell it I had a header row. So I have to go into sort range and say my data has a header, sort temp. There we go. So now they're in order. My count here, according to my computer over here, says there's 7 items here. So let's see, 7 plus 1 is 8. 8 divided by 2 is 4. So the 1, 2, 3, 4th item should be the median. So what's that? There, yeah, and then here's the question, well, which 98 is in the middle? Well, it turns out one of those 98s belonged to, I think, Ian, another one belonged to Adrian, another one I think belonged to Justin. So one of you is that 98, right? Because they are different, they belong to different people, even though they are the same value. So whoever that ended up being, I lost track of whose it was now. But that one's the median. And it really doesn't matter whose it was, but it is the median. Let's see, and then we have a 97.4, 99. Does this data look like it's spread out in an awkward way, or does it look kind of balanced? Looks kind of balanced. So when we calculate the mean, it shouldn't be too far off, right? Okay, so whip out your calculator, find me the mean of those numbers right there. I'm going to ask the computer to do it for me. On the computer, you just say, hey, give me the average. Computer says you should get about 98.1. Okay. And again, if there were 100 or 500 numbers, we don't want to do that by hand, right? We want them in a spreadsheet. Spreadsheet does the calculations. So we'll jump in the lab and do spreadsheet stuff earlier. So that kind of fit our intuition. The data doesn't look like it's skewed one way or another. It looks about balanced, and so the median and the mean should be pretty close together. Okay. Since the mean is slightly higher, that means there's a little more bulk to the right of the median than there is to the left. So the numbers on the right are probably a little bit more spread out than the numbers on the left. And we could graph them to kind of see that. So we're going to do a different calculation next. And this is kind of weird. Calculating quartiles. So a median means 50% is below, 50% is above. The first quartile means a quarter is below, 3/4 is above. The third quartile here would mean that 3/4 of the data is below that point. Quartiles only work out well if you have exactly 100 numbers, because we're talking about a percentage of data. Will we always have 100 numbers? No. Sometimes we have more, sometimes we have less. So picking which number gets to be the quartile is always awkward. And it turns out there's no one way to do it. So Adri's calculator does it different than Google Sheets. Other statistical software out there does it different than Sheets or her calculator. And then when people do it by hand, there's various methods. Okay. So there's a method in the book that the homework problem I picked happens to require you to use, so I apologize for that ahead of time if you haven't done it yet. And I want to bring that up here. So we're going to try and implement the method, then we'll compare it to the computer method, and we'll see they don't quite match. Let's see, where's the book? There it is. Okay, so on page, it's probably labeled 267, depending on where your printout came from. It talks about what quartiles are. And then at the bottom of that page, this where it has the L's here, that's called the locator method for finding quartiles. So we're going to try and implement the locator method. So I'm going to copy this method into my sheet here. If I can find my tools. There they are. And then I'll get the data and we'll try to do this, see what happens. So here is the locator method. So if you have your book, you might want to open to this. 267 is the page number, if you get the printout from the same place I did. And then my data is right here, so we'll screenshot that. So I only need the numbers. Okay. So the way the locator method works is to find like the first quartile. Reminder, first quartile means 25% of the data is at or below that point. There we go. So usually it's abbreviated Q with a subscript 1. Sometimes subscripts are a pain to write, so we just call it Q1. Okay, and it means the data value where 25% of the data is at, oops, or below that point. Okay, so the locator method says take, because we're looking for the first quarter, take 25% of the number of data elements you have, all right? Let's see. So that means for our location, we want to take 0.25 times 7. So let's see, half of 7 is 3.5. Half of that is like what, 1.75? Okay, so then it says if this is a decimal, round it up. And then use that number. So this number right here, according to the locator method, is Q1. So I look for the number in that position, right? Because the location is the position. Now, what if there were 8 numbers in the list? Well, if there were 8 numbers in the list, let's see, what's 1/4 of 8? It's exactly 2. Locator method says if you got exactly a whole number, then you average that position in the next one to get your quartile. Why? Well, because somebody thought this was a good idea. There were other ideas on how to do this, but that's the way to do it. Okay, let's apply that. Now, this is the first quarter. We're going to find the third quarter. The median is the second quarter. So couldn't we apply the locator method to the median? Yeah, we should be able to because it's a quarter. It's the second quarter. So just for fun, let's see, if I were going to apply the locator method for the median, I would say the location would be not 25%, but 50% of the number of items. Okay, right? Because here, first quarter, 25%. I'm looking for the second quarter. That should be 50%. Okay, half of 7 is 3.5, right? And the locator method says if it's a decimal value, grab the next whole number, which would be, okay, so according to the locator method, 1, 2, the fourth number should be the median. Does that match the method I gave you earlier? Yeah, so it turns out the locator method is similar to the idea I said how to find median before. Okay. And guess what we're going to do to find the third quarter? Instead of 0.25 or 0.5 times the number of things, it's going to be 0.75. Yeah. Yeah. So let's see, I can squeeze that underneath here. So the location for Q3 should be 0.75 times the number of things. And that's going to be what, 5.75? Anybody with a calculator? 0.75 times 7? 5.25. Oh, I was off. Okay. And 5.25 is a decimal, and the locator method says round that up to 6. That's the position you want to look at to get Q3. So I'm trying to find the location of Q3 right there. All right, let's see. 1, 2, 3, 4, 5, 6. That guy right there should be Q3. Adri, do you know how to use the statistics on your calculator? May I borrow your calculator for a second? So Adri has a TI 84. And so I'm going to type these numbers into her calculator. And I'm also going to do it on the spreadsheet here in just a sec. So let's see, statistics, edit, list. I want 97.4, 97.9, 98, 98, 98, 98.3. For those of you on the internet, sorry, Fen, this is kind of boring. I'll tell you what I get in just a second. Okay, so I entered the numbers into a calculator, and then I'm going to ask the calculator to do some calculations for me. Okay, calculator says the first quartile should be 97.9. Oh, TI agrees. It says the median should be 98, and quartile 3 should be 98.3. So it could be the calculator is using the locator method to find these. All right, now, so the calculator agrees with the locator method. Let's go ask Google Sheets what it thinks. So Google Sheets, so off to the side, I have a place for me to do the quartile. So I am going to type equals, and then I'm going to start typing quartile. And hey, check it out, there's a quartile command. So I click on it, and it says, where's your data? Right here. Comma, and then it says, which quartile do you want? And it says, how about 3? No, I don't want the third quartile. I want the first quartile. So I type a 1 for first quartile. So then I type a 1, and then I hit enter, and it says it's 97.95. That's a different number. Okay. So thing to keep in mind is there are many, if you look out on the internet, I found like 3 or 4 methods that are popular out there in different software packages. So not every software package will give you the same quartile for the same set of data. They'll be close, but not the same. So what? Okay, it's just a mark of relative position. So if I wanted to find quartile 3, I would do a similar thing. I would start typing quartile. I would highlight my data. And in this case, I would do a comma 3 for the third quartile. Now here's the cool thing about quartile. The quartile command accepts for which quartile you want, 0, 1, 2, 3, or 4. What? Why the hell would it do that? Quartile. So the min would be quartile 0. Quartile 1 is obviously 1. The median would be quartile 2, right? 2 quarters is half. Quartile 3, and then the max would be quartile 4 because 100% of the data is at or below that point. So although quartile 1 and 2 are pretty popular, the computer command actually has 5 different options, and they will give you min, quartile 1, median, quartile 3, and max in that order, which is kind of neat. So we have an option. We don't have to use the median command. Instead, we could just go, hey, give me quartile 2 for this data. And it will agree with what the median command tells me. Yeah, you could use one formula for a whole bunch of stuff. Yeah, so instead of min, max, median, and quartile, you could just use quartile to get all of those. Now, these numbers right here, these 5 numbers that I'm about to get, those are what are called the 5-number summary. So let's highlight them, make them pretty. Let's see, where's my highlighter? How about a nice light green, because it's a beautiful fall day. So the min I could get in one of 2 ways. I can say, hey, give me the min. Here's your data. Now, often our data will be sorted and we can just look and find the min. Similar for the max, but what if there's a million numbers on my list? Do we really want to scroll to the end of the list? Not really. So it's best to use some kind of command. And I could either use the max command, data, or I could use the quartile command to get that. So just double check. If I said, hey, quartile for the data, but I want the 4th quarter, which means 4 quarters, 100% of the data is at or below that point, it should give me the max. Okay, same result. So sometimes in a spreadsheet, you have options on how to do your calculation. Okay, so again, that's the 5-number summary. We'll do, oh yeah, let's do something with that right now, actually. This is kind of exciting. Let's see, I need to copy that to my sheet. New page. Often, in statistics, we like to draw pictures. So I'll show you how to draw a picture of the 5-number summary. Sounds kind of lame, but it's actually pretty exciting. Let's see, where's my screenshotter? Come on, screen clipping. Okay. So to draw a picture of the 5-number summary, what you do is you draw a number line, and then you mark the numbers off on the number line, but placed right. You got to place them in the right spot. You can't just throw them wherever you want. So I'm going to make a number line here. And let's see, my numbers range from 97.4 to 99.4. So they have a range of 2. Right? So maybe on my number line, I will start at, say, 97 over here. Let's put 98 here. 99 there. Is that about the same distance apart? No, it doesn't look good. All right, graph paper is always nice. All right, maybe I need, let's see, we'll use my hand. Okay, 97, 98, 99, 100. So then what I want to do is place each of these numbers. And so I'm just going to use a different color to place them as best I can. So 97.4 is just below the midpoint here, so maybe about right there. And then let's see, first quarter is 97.95 if I use the computer method. If I use the books method, what was it? It was something else. It was 97.9. You know what? On this number line, I can't tell the difference between those 2 numbers, 97.9, 97.95, so it's kind of moot. Pretty darn close to 98 here. So let's say about right there-ish. Then the median is 98, so right here. And the third quarter, 98.15, that's right about here. And then 99.4, way over here. Did I put those in the right spot, you think? Okay. So what you do with these numbers, that's not a very exciting graph, is it? To make it more attractive, what you do is you draw a box. Oops, my pen is mistracking. You draw a box around the quarters with the median marking the center. Oh my gosh, let me fix my pen, hang on. See if I can draw that a little bit better. Do those last few pen strokes. So you draw a box around those. That's a little better. And then you draw a line out to the min and the max. And so when you plot the 5-number summary, it's called a box plot or a box and whisker plot. And so there are software packages that do it automatically. Unfortunately, Sheets and Excel don't draw them. TI does, which is kind of cool. So otherwise, what I'd usually do is if I don't feel like drawing it myself, I go out to the internet and I search box plot maker. And there's a bunch of websites where you just plug in your data and it spits out a graph of it. Okay. But we'll make a couple by hand next. All right, so that's called a 5-number summary. So in a little bit, what we'll do is we'll make a and what's interesting is to plot a histogram with the 5-number summary, because together they show some interesting things. Now, unfortunately, I only have 7 numbers. It's not worth making a histogram out of 7 numbers. Okay? So we need more numbers. So we'll get more numbers in a minute. But I want to do more with these 7 numbers. All right, so here's what I need you to do next. So you're going to follow along with me partially. So I'm going to show you a hard way to do a calculation, then we'll do it the easy way. Is that okay? You guys sound thrilled about that. All right. So who in here's temperature was average for this class? A couple of you were 98, right? Okay, but the rest of us weren't. So mine was kind of low. Okay, so yours isn't too, yours is a little high compared to average, but 98.3, mine 97.4, so I'm 0.6 below average, you're 0.3 above average. So when somebody isn't average, they deviate from the middle. Okay, and it turns out deviation is a popular statistic to calculate. Okay, so to calculate deviation, what you do is you just take the actual score, temperature, whatever it is, and you subtract from it the average. Oh, our average is 98.1, sorry. Okay. That's deviation. And so I just wrote a formula that I can then fill down and I can get everybody's deviation. Now here, since nobody was exactly the average, because the average was 98.1, there we go. Everybody has a deviation. So deviation helps talk about the spread of the data. So there's a few ways to talk about spread of data. So one way to talk about spread, and we did this the other day, was looking at the range of data. Range is always the max minus the min. Okay. Other way is the 5-number summary. Which is more helpful when you turn it into a box plot. Okay. So that helps us talk about the spread of the data. Deviation also helps us talk about spread. The problem with deviation is if there are 1 million numbers in your set, that means there's 1 million deviations, right? We can't just look at them and say, oh yeah, look at that, all that deviation, right? That's not helpful. So somehow we have to summarize the deviation. And so there's a couple of ways to do that. So we want to try to find an average deviation. Okay, so watch what happens when I go to find the average deviation. So underneath here, I'm going to calculate average. Another word for average? Mean. On a computer, though, it's average. Average. There you are. And then I highlight the numbers I want to find the average of, my deviations. Now we know what the average temperature is, right? That's 98.1. But check out what the average deviation is. 0. Why? Well, because we were finding how far things are from average. Some things are above average, some things are below average. Isn't the average the middle? Yeah. So there's no surprise there. On average, deviation is 0 because average is the middle. Another way to think about average, if that was money we were playing with here, if I took money away from the rich and gave it to the poor until they both had the same amount of money, and I did that for everybody, how much money would everybody have? Well, they would have whatever the average was before, because it's still the same amount of money. Because remember, what is average? It's the sum divided by the count. Okay, so we have a problem. Every data set on Earth has an average deviation of 0. But somehow we need to summarize the deviation because they help us talk about spread. So people came up with a couple of techniques for doing so. The most popular is what's called the standard deviation. Okay. And that's what we will use. There's another kind that's used in some books, but I refuse to use it, but I will mention it briefly. Trying to remember the name of it now. I blocked it out because I find it so offensive. Because it turns out that if you try to use it to predict anything with statistics, it doesn't work very well. Yeah. I think it's called mean average deviation. Is that right? No. It's mean absolute deviation. Absolute as in absolute value. Unfortunate abbreviation of this, MAD, don't use it. It's introduced in some books because it's easier to do than standard deviation, but in practical applications, it is not useful. Okay, so if you ever see it in a book, just skip over that part. It's not worth it. Standard deviation. So here's the technique people came up with. What they said is, okay, the signs are the problem. But somebody quickly figured out that you can't just strip the signs. That's absolute value. That messes stuff up. So what they decided to do instead is square the deviations. So they take the deviations and they square them. So on my computer here, I'm just going to take each of these numbers and raise them to the second power. And so what I do is I take the squared deviations. And then what you do is you average those guys. I'll write all this down. It's in the book. But I'll show you the easy way in a minute. Okay, so then I average those suckers. Average way. Oops. Now, although I have a nice number here, the problem is it's the average of the squares of the deviation. Well, shouldn't I try to get rid of the square somehow? What's a popular way of getting rid of a square? Take the square root. So then we take the square root of that after we average it. I take the square root of that number, and this number that I end up with that's what's called the standard deviation. The number I found before is what's called the variance. Variance isn't that useful, but it's kind of useful, but not really. Standard deviation is way more useful. So this number right here is very important. So let's highlight that in yellow. Ooh, not that way. Okay, reset. I meant to do over here, highlight. There we go. Yellow. Ah, there we go. So it turns out there is an easy way to find the standard deviation on a computer. By hand, that's what you got to do. Okay. So before graphing calculators, when I took this class, Excel wasn't out yet. I had to crank all this out by hand. So I had to do that. Pain in the butt. Then spreadsheets came out, and someone says, hey, this is a computer. Computer can do repetitive tasks. We'll do it for you. So the computer, let's put it here. You just type STD, and then you take your pick. Which STD do you want? I mean, standard deviation. Not sexually transmitted disease. And there's a whole bunch of them here. Micaiah, she didn't even laugh. She's asleep. Come on, honey. We're having fun with STDs. Come on. Let's go. All right, so there's one called STDEV. There's another one called A. Oops. Oh, I meant to just have it. A, there we go. That says standard deviation of a sample. If you put a P at the end, that's a standard deviation of an entire population. And then PA is standard deviation of a population, but if there's any text that you highlighted, it treats it as 0. Okay, it doesn't ignore it, it treats it as 0. That's different. Ignoring something versus treating it as 0. So you got to be careful which one you pick. Usually, do we have a sample or the whole population? We usually have a sample. Yeah, it's hard to get the whole population. So usually we have a sample. And so it turns out STDEV and STDEVA are actually the same command. Okay. I was treating the data as if it were a population. So for me, I'm going to choose P because it's going to confirm the thing I did by hand over there. So I choose the P, I highlight my data, and I hit enter, and I should get the exact same number. Is it exactly the same? Oh shit, it's not the same. Oh, it should be the same. I don't know. I lied somehow. P, that should give me the same number. That is weird. A should not give me the right number. Yeah, that gives me a different one. Huh. How did I screw that up? You know what's really funny? I did this before, and it works just fine. Something about AJ's candy, it's messing it up. Okay, let's see. Double check. I took the deviation. Oh, do I have the right average? Oh, check this out. I bet I know what the problem is. I wasn't using the exact mean. The mean has more decimal places, and the computer wasn't showing them, and I just used 98.1. So my calculation's a little off. So if instead here, instead of typing 98.1, I say, hey, use this calculation as the mean, I have to fix row 10, and then I fill that down, then they should match. Oh, good. Okay. So I didn't lie. Sorry. So, but usually what we'll do is the other one. So the other one, if I do that, STDEVA, highlight your data, hit enter. Way easier, right? One shot. This is called the standard deviation of a sample. That's sample STD. You always have to be conscious. Which one do you want? Default, use the sample version. It's probably the one you want, okay, with the A on there, or without the A. Excel is slightly different. So if I bring up Excel, for those Excel people here, blow it up. STD, I forgot to type equals, STD. So they have a bunch of issues. They put dots on theirs. So they have an STDEVA, which is just like the one in Sheets. STDEV.S is the same thing as STDEVA. And the only difference between them really is whether they ignore text or not, if they treat text as 0. So you just got to think about that depending on the data you highlight. So usually in Excel, you would want STDEV.S or STDEVA are the two you would want. And I can't blow that up anymore, sorry. Excel won't let me. All right, so moral of the story, deviation is important. It's how far an individual is from the center. We need to average that somehow, and the correct way to do it in this day and age is to use what's called the standard deviation. And fortunately, spreadsheets and calculators have a button for it. Push the right button. And you don't have to do all this crazy stuff like I did there. Okay, so, oh, the button on your calculator, by the way, if you hit stat, calc, if you do the one variable statistics, it does all of the data that we want. So hit enter, and it says, do you have any data in list 1? I just put data in there, so go down to calculate and hit enter. And then it will give you a whole bunch of stuff, and the arrow means there's more stuff underneath. Okay. Okay. So next, we need to take a look at a more exciting histogram. Oops, wrong button. Go away. So the problem here is we have too few numbers. Okay? So I have a sample of 50 numbers here that I'll mess around with. So these, again, are human body temperatures. And the first thing I do when I get a set of data, no matter how big and how small, is I do a few basic calculations. So right away, I want to know how many there are. So I want to do a count. I'm also going to want the 5-number summary. So I want my min, min. I want my Q1. I want my median. I want my Q3. I want my max. And then other things, and let's separate these a little bit. Other things I want are the mean and the STD, standard deviation. And I just asked the computer to do all those for me. So this is going to be a little boring while I demonstrate this. I'll have you go to the lab and do this in just a minute. So as far as count goes, I can take somebody's word for it to look and count myself, but really what you want to do is use the count command to double check that you do have what you think you have. Highlight all of your data. Count says, yep, you have 50. Min is pretty similar, equals min. Highlight your data. Sheets got clever recently. You don't even have to type the closing parenthesis, although Excel usually freaks out about it and says, hey, you forgot the parenthesis, please fix it. Google just fixes it for me. Quartiles, the quartile command. A quartile command requires 2 inputs. It wants the data, and it wants to know which quarter you're looking for. So right now I'm going to say 1 for first quarter. Yeah. Median is the median command. Pretty straightforward. Highlight. Q3, again, quartile, data, and then like AJ said, I want to do a (3) for the third quarter, and max is just the max command. Command for mean, anybody remember?
Average.
Average, there we go, a couple got it. Average, and there's a bunch of different kinds of average. We want the one just called average. Highlight your data. STD, which one do you think I want here? A, because this is just some people's temperatures. So I highlight those. Okay, so that's the first thing I do with a set of data. Second thing I do is I make a histogram. 2 ways to make a histogram. One is to highlight your data and have Google make it for you, or do a frequency table. Since you're asked to do frequency tables for the homework, and I think they are important, I'm going to do it that way. So then I need some space somewhere, and what I want to do is have my bins, my categories, and then I want to have my frequencies. So first we have to decide, well, okay, how many bins do we want? Or how wide they are. We have to choose one or the other. Now here my data ranges from 96.5 to 100. So what's that, 5.5? No, 3.5. So it has a range of 3.5. So sometimes it's not bad to calculate the range on the screen just to see it. And oops, range. And the only way to calculate the range is to take the max and subtract the min. Okay, so 3.5. So I need a bunch of bins that cover a range of 3.5. So let's see, if I went by 0.5, that would give me 7 bins. That might be all right. Starting at just before 96.5. So maybe I'll have 96.5 be the end of my first bin. What should my second bin then be then, max? If they're 0.5 apart?
97.
It should be 97. Once you have the first 2 bin maxes, you can just fill them down to get as many as you need. Okay. So I don't need that last one. Then what do I do next? Anybody remember how to make a frequency table?
Equal.
Highlights.
Oh, highlight first.
every cell next to a bin plus 1, okay? And then you just start typing equals frequency. Enter on Sheets, tab on Excel to complete it, and then you highlight your data. That's not my data. There's my data. Comma, and then I highlight my bins. In Sheets, what do I do next? That's in Excel, it's Control-Shift-Enter. In Sheets, it's just Enter. Okay, and so there's my stuff right there. Now, if I go to graph this right away, I have one problem. Let's see, chart types. I just want a bar chart. Why is it giving me column A as labels? No. Oh, wait. Yes, column A is labels. Row 13 is not headers, though. Huh, why did it give me one extra one there? That shouldn't be there. Well, they should all be equally spaced, and I got this one. Oh, one of them had none in them. Okay, yeah, thank you very much. All right. So the main problem with this is the bottom is not readable. Okay, so I have to go fix that. So let's see. Customize is right there. And let's shrink this so you can see what I see. And so what I have to do is I have to, let's say I can turn off the legend. And then down here, I want to tell it to treat labels as text. That kind of helps. But what does this mean? That there were 10 people who had a temperature of exactly 98? No, so this graph is misleading right now. What do I have to do to fix it? Think back to Monday. Well, you could change it into points, but that still doesn't exactly help. Because what this 3 means is that there are 3 temperatures 96.5 or less. Here, this tells me there were, let's see, 2 temperatures that were higher than 97 but lower than 97.5. Yeah, so what I need to do is, so even points wouldn't help here. I need another column for human readable bins. Remember we talked about that the other day? Yeah.
Mm-hmm.
Okay, yeah. Oops. I messed it up. Yeah. So what I need is I need a better label here. So really what this should be right here is, let's see, I'm going to do the next one. 96.5 is the max for that bin, right? That means the next one starts at 96.6 and goes up to 97 for the human readable bin there, right? And then the next one, where does it start at? No. 97.1, it has to pick up where this one left off. Let me blow it up again. Yeah, so this one ended counting at 97, so this one picks up counting at 97.1 and goes up to 97.5. And then this next one is going to be what? 97.6 up to, oops, I missed my 7, up to 98. Okay, so now backtrack. What should the first one be? Well, technically, because the computer's counting that way, but our bins really should be all equal width. Look at the pattern here, 96.6, 97.1, 97.6. What's the next one going to be here? 98.1 up to 98.5. So run this pattern backwards. What should this be? 96.1. There we go. We got a winner. Yeah, up to 96.5. So writing the human readable bins is a pain in the butt, but you got to do it to make your graph readable. Without it, your graph doesn't make any sense. So this would be what, 98.6, 99, 99.1, up to 99.5, and then 99.6, up to 100. And the more category is just there to make sure we didn't miss anything, okay? And so this is what I should use to make my chart. So that it's labeling each column. Now, if you don't like the orientation of them, you can put them at an angle instead. So there's lots of ways to pretty it up after that. But bottom line is, when you make a histogram, do it on a computer. First step, you do the bins and you do the frequencies. If you have a decent histogram based on that, then write your human readable bins. Okay? But how do you know what the best histogram is? Does anybody remember from last class? Make a bunch. Yeah, there is no best histogram. You just got to make a few and then say, okay, I like this one because, and have some kind of a reason. Okay. If you can't come up with a reason why one is better than the other, then whichever one is visually more appealing to you, pick that one. But you got to make a couple. Okay. Google does give us a quick way to make a histogram, but all the data has to be in the same column for it to do it. Okay. So I'm going to just back up to a different sheet. On the home page here, I gave you a bunch of body temperatures. In the next one over, I just randomly picked 50 of them. So with Google, I can just highlight this column. There's like 519 of them in there. And I can go to more and say, hey, give me a histogram. And Google says, okay, here's a histogram. Let me shrink this down. Now it picked a lot of bins. That's kind of more than I want. So then I go over to customize. And remember, they're called either bins, categories, buckets, groups. So then I say, I want a different bucket size. And so here, what does the bucket size seem to be? 99.45, 99.75, 0.3. So maybe I'll do like 0.5 instead, like I had on my other one. Oh, okay, yeah, that looks pretty good. And if you don't like that, try another one, 0.4. So Google gives you a quick way to make a whole bunch of histograms and say, oh, okay, I think I'll go with this one over that one. Maybe 0.45. Ooh, that one looks kind of cool. 0.6. Maybe 0.2. Oh no, not that one. 0.1. Oh, definitely going the wrong way, right? So that's one nice thing. So then once I have that, then I can redo it with human readable bins that'll make sense to somebody. Because even Google's nice ones here, the numbers on the border, it's not clear whether 97.2 represents the largest acceptable number for this column or the smallest acceptable number for that column, right? That won't be clear to the reader. And some people do it one way and some people do it the other. So although this is a great quick histogram, it's not completely clear. You would have to have some kind of note that says, this is how I did it. Okay. So we'll worry about that later. I'll talk about that in the next class. All right, we covered a ton of stuff here. So what I want to do next is set you into the lab. And what I'd like you to do is I have this body temperature sheet set up here for you to use. I'd like you to open up in either Sheets or in Excel, your choice. I'd like you to do the 5-number summary, and I'd like you to make at least one histogram. And next class, what we'll do is play around with comparing histograms to box plots and see how they tell us stuff together. All right, that's it for now. Let's see, Fen, have you had a chance to play around with this stuff? So the rest of you go grab a computer.
Yeah, I did when you were doing. How do you sort the number from small to big?
In Sheets or Excel?
In the sheet.
In Sheets. So if I have a set of numbers that aren't sorted, like my temperature one, what I do is highlight, say, that column, and then I go to the data menu, and I say sort range. In sort range, in this case, I do have a header called human body temperature. So I would click, yes, I have a header. And then I choose sort those numbers.
Oh, it just automatically go from small to big.
And it will go to small to big. If you wanted to go the other way from largest to smallest, you go back to sort and you change A to Z to Z to A instead.
Okay, I see.
And so I can sort it reverse order also.
Mm-hmm. All right. I have one more question from
Sure.
written assignments. What should I do to do the citation better?
Oh, on that one, let's go back and take a look. Hang on.